One GCSE student, one year 11, asked me the other day to do a short video on when we might see and use ionic equations and half equations at GCSE. These are ideas we come back to in quite a lot of detail in sixth form, but we have to be aware of them at GCSE as well. Now, the couple of places where you're most likely to see ionic equations are when you've got neutralization going on with an acid and an alkali. They like to ask this question quite a lot, and all that's going on there in the neutralization is that hydrogen ions from the acid and hydroxide ions from the alkali are combining to make water. It's the same reaction regardless of whether you're using hydrochloric acid, sulfuric acid, nitric acid, any alkali. It could be sodium hydroxide, lithium hydroxide, calcium hydroxide, whatever, but in the end it boils down to that reaction. So you should know that reaction for neutralization. And all an ionic equation is showing you what's really going on. So I don't want to get into this in too much detail, but if, let's say, we took hydrochloric acid and sodium hydroxide, you've learned that you would get salt plus water. We'd end up with sodium chloride, AQ, plus water. Now, when a strong acid, HCl, is dissolved in water, what you've really got is hydrogen ions and chloride ions, because strong acids fully dissociate. Sodium hydroxide does the same thing, it fully dissociates the sodium hydroxide, sodium ions and hydroxide ions. And when a salt, sodium chloride, is fully dissolved, it's sodium ions and chloride ions that are separate from each other, because you know that when the ionic compounds conduct in solution, don't you? Because the ions have broken apart from each other, the ionic bonds have been overcome, the ions become surrounded by water and they can flow and all that stuff. And then there's water. If you look at that equation carefully, you'll see that chloride is the same on both sides, so it's not really changing during the course of the reaction. Well, it's not changing, we call it a spectator ion. That's the same for sodium as well, and we end up, as I said, with H plus 8 OH minus hydroxide goes to water. It's the same every time, regardless of what acid or alkali you use. So that's one example of an ionic equation that might be worth a mark. Make sure you know what the state symbols are for that. And another example of an ionic equation you might see is when we do displacement reactions. So this could be something like, you know that if you take a reactive metal like magnesium and you put it into something like copper sulfate, the magnesium, being more reactive than copper, will displace copper from copper sulfate, give you magnesium sulfate, write it out, and copper. So what, I'll just write that out quickly. So you've seen and know this balanced equation. Solid magnesium, which is more reactive than copper, will displace the copper to give you magnesium sulfate and copper, and that's fine. But really all that's going on there, the sulfate's not doing anything. Copper sulfate dissolved is copper ions and sulfate ions. Magnesium sulfate dissolved is magnesium ions and copper ions. And so what's really happening there, the copper ions react with the magnesium atoms, magnesium metal, to give magnesium ions and copper. So that we're just taking away, we're ignoring the sulfate, which during the course of the reaction isn't being affected. So this is what we call the full balanced equation. This is the ionic equation. And another example which is similar to that is another displacement reaction. In the group 7 topic, you have to know that more reactive halogens like chlorine, when dissolved in water, so chlorine water will react with potassium bromide solution to give potassium chloride solution, and bromine dissolved in water, that's meant to say AQ there. But really all that's going on there is that the potassium bromide and the potassium chloride are dissolved, which means the potassium ions and the bromide ions, or the potassium ions and the chloride ions, are separated apart from each other. So the potassium is not changing or doing anything in that reaction. So the ionic equation, if I put ionic equation like that, is simply the chlorine water reacting with the 2 bromide ions to give you 2 chloride ions and bromine. So that's all that's happening. Remember, in that equation, or in that reaction, the bromine water is quite dark coloured, it's orangey coloured compared to the very pale green of chlorine. So that's evidence that chlorine is more reactive than bromine, isn't it, as well? But these 2 equations are also examples of what we can consider when half equations can be used. Now, half equations show what's happening in redox reactions. So in all redox reactions, you've got some sort of reduction, so gain of electrons, and an oxidation, which is loss of electrons. So as you go from copper to copper, as you go from copper 2+ to copper, the copper 2+ is gaining electrons, which is out, and magnesium is turning into magnesium 2+ ions. So we can write those as 2 separate half equations. So I'll do that down here. The copper ions are gaining electrons, so that's 2 lots of electrons, AQ. Become copper, that's reduction, and the magnesium ions are oxidized, magnesium turning into magnesium ions. And when you're working out with half equations where to put the electrons, either work out whether it's reduction or oxidation. If it's reduction, the electrons go on the left, oxidation on the right. But one way I like to remember it is wherever if I know copper is turning into, if copper is turning into copper 2+ is turning into copper, I put the electrons on the side which is more positive. The electrons go there, and overall now both sides have the same charge, 0 charge on the left and 0 on the right. And likewise with the other one, the oxidation, and if we've got magnesium turning into magnesium 2+, stick the 2 electrons on the side which is more positive. We could have done the same thing for this reaction, so I'll just put a little line there. So this reaction can be written as Ionic equation as well, where chlorine is turning into chloride. So use that same logic, we put the electrons on the more positive side. The more positive side is the left hand side, which is 0 charge. The right hand side is overall 2- charge. So put the electrons on the left. And the bromide in that equation up here is turning into bromine. When I say bromine, I mean Br2. Where do you put the electrons? Put them on the more positive side, so electrons go there. So we can write these ionic equations out as half equations. And we've got reduction here, oxidation here is reduction because it's gain of electrons, oxidation because it's loss of electrons. You also see half equations when doing electrolysis, so do get your head around electrolysis, do spend time on it. But electrolysis, remember, and we've got reactions happening on the surface of the electrodes. And we always, in those cases, are generating elements from ions. And at the cathode, sorry, the negative electrode, we might be producing either hydrogen, which we've covered in other videos at other times, or we might be producing an unreactive metal like copper, and the hydrogen will be made from the hydrogen ions that are in solution, and the copper might be made from the copper ions in solution. So to balance those half equations, let's have the same number of hydrogens on each side. There's 2 hydrogen atoms over here combined together in a hydrogen molecule, so we must need 2 hydrogen ions, and we put electrons on the more positive side. 1 copper turning into 1 copper, but just put the electrons on the more positive side, so that's reduction, and reduction happens at the negative electrode. And that makes sense because the positive ions go to the negative electrode in electrolysis. Or for the oxidation that happens at the negative electrode, we might be forming the elements. It could be, if it was, say, molten aluminium oxide, we might be producing oxygen from oxygen 2-, or it might be we're producing chlorine gas from chloride ions in aqueous sodium chloride, for example. or it might be we're producing oxygen from hydroxide ions. And that might happen if you've got, say, copper sulfate, and it's the hydroxide ions from the water that are turning into oxygen. So let's balance those half equations. We've got 2 oxygen atoms, so we must have 2 oxygen ions, and we stick the electrons on the more positive side. The left hand side is 1, 2 times 2, 4 minus, so we need 4 electrons. Over here we need 2 chlorides, just the reverse of the equation we wrote on the previous page. 2 electrons over here, electrons on the more positive side. This one's quite a difficult one. I'd encourage you to either learn this or practice this. But the thing to remember really is that water is also produced, and if you can remember that, this equation becomes possible to work out. Now you can see, you might be able to see quite quickly that you're going to need a bit more hydroxide. If you have 2 hydroxides to match up with the hydrogens, you end up with the wrong number of oxygens. And the only way to really make this work is if you have 2 waters produced, 4 hydroxides therefore needed, so 1, 2, 3, 4 oxygens, 1, 2, 3, 4 hydrogens on both sides. Stick the electrons on the more positive side. Job done. So they're examples of when you would see half equations and ionic equations in your GCSE. Also, I'd encourage you, just for the last thing, to look up, and I'm not going to do them here now, but there are some half equations you would know for fuel cells. I'm going to do a separate video on fuel cells as well. Hope that's useful. Cheers!